Welcome to Revise for Physics, the place where you revise for physics. Some of the cheesiest revision videos on the internet. Hi, in this video I'm going to be talking about nuclear binding energy and how energy is released by fission and fusion. So this comes from two specification points from the Edexcel specification, but they're really common across all specifications. So it's this idea of what nuclear binding energy is and how nuclear fusion and fission release energy in relation to the binding energy per nucleon curve, also known as the nuclear binding energy curve. So we start off with a basic idea, and that is that if you took individual nucleons in a nucleus and looked at them and the forces holding them together, they're held together by the strong nuclear force. If you wanted to pull the nucleons apart, then what you would have to do is you would have to do work or expend some sort of energy on these nucleons to pull them apart. So that means that if you're forming a nucleus from free individual nucleons, then energy must be released. That's the opposite process. So energy needed to pull them apart, energy must be released in bringing them together. So this energy, known as the nuclear binding energy, comes from the original masses of the individual nucleons and is released by the mass of nucleon decreasing slightly. So the mass decreases as the nucleus is formed. So this reduction in mass is known as the mass defect, and the energy released is described by Einstein's equation, E equals mc squared. Exciting. Finally, possibly using that equation for the first time. Now I'll show you how you can use it later on in the video. But here it is, the big exciting nuclear binding energy curve. So the curve has some important features. Now it starts off with 0 because hydrogen as an individual proton doesn't require any energy to hold the protons together, or doesn't release any energy as the protons are held together. But that's just because it's not held to anything. So this is the starting point for any protons and neutrons. And then as you combine them, initially energy is released as the nucleus becomes more and more stable. But beyond the point of ion, the nucleus becomes less stable because the strong nuclear force is trying to fight against the repulsive forces, the electrostatic forces from the positive protons, and the strong nuclear force is only a very, very short force that acts only over a short distance. So rather than getting stronger and stronger as the nucleus gets bigger and bigger, it starts to get a little bit weaker towards the edges. Or at least the balance of the forces means that these nuclei here are more unstable, and by unstable that means not as energetically favourable. So we have heavy nuclei here, we have things in the region of iron and cobalt here, and here we have the smaller, lighter nuclei. Now there's a handy little feature here, and that's that helium is a bit of an anomaly. It's very, very stable, and carbon and oxygen are also anomalies. So that means that there is a lot of helium being produced, and it also is the reason why or at least in my opinion, why the release of a helium nucleus or an alpha particle is so energetically favourable as opposed to releasing free protons and neutrons. It's also the reason why there's lots of carbon and oxygen formed in nuclear fusion, and also why stars are filled with iron. They produce iron. So in this part of the curve, you see where energy can be released through nuclear fusion, taking these smaller nuclei and fusing them together will create larger nuclei that are more energetically stable and will release energy. If you wanted to take nuclei from this region and fuse them together to make nuclei that were bigger, then that would require giving them energy. Okay, that process is a process that absorbs energy, known as an endothermic process. Not just limited to chemistry there, that term. Whereas converting heavier nuclei into lighter nuclei is an exothermic process, as it releases energy as the nucleons move towards this point on the binding energy curve. So the nucleons lose mass from here to here. Okay, and again from here to here, the nucleons will lose mass. So this part of the curve represents where energy can be produced through nuclear fission, and here through nuclear fusion. So here, when we look at the binding energy curve, you can see the basic features that we talked about again. And now if we put it into practice, we get these two components. You've got the surprisingly stable section of helium. We've got over on the left where this energy is released through fusion, and then we've got the basic of the fission process. And it's that fission process that I'm going to look at now, where I'm going to take this exam question and just solve it. So we start off by just filling in the numbers. An alpha particle has a mass of 4 and a proton number of 2. I use that proton number to fill in the proton number of the americium, and I use the nucleon number to fill in the total mass. Now, this part of the question really illustrates just how small the change in mass is. When we want to do calculations with the release of energy, we need to start off with the mass of the original nucleus, the final mass of the nucleus, or the two nuclei, because here we're considering an alpha particle to be a particular nucleus. Now, in doing what we're doing, we're using these tiny numbers, or tiny changes, but those tiny changes in mass are quite significant, because obviously in Einstein's equation this is using E equals mc squared, so c squared giving you 9 times 10 to the 16 is a very big number, and that's for every single nucleus that decays. So basically large amounts of energy can be released even though there's only a small change in mass, and it's a small change in mass that's not even noticed that much. Now, the change in mass is simply the original mass subtract it, and then you take away the other masses. Right, pardon my handwriting here, but here are the steps. So if I take away these masses, then I should get a final answer for my change in mass, and my change in mass here I've worked out to be 0.006053 U. Okay, now U is the atomic mass unit, U for unit. It's very original. So that change in mass is 0.006053 multiplied by 1.66 times 10 to the minus 27 kilograms, okay, because one atomic mass unit is 1.66 times 10 to the minus 27, or one nuclear mass unit. So that gives me the very small number of 1.005 times 10 to the minus 29, and so my energy is E equals mc squared. Yay, I get to write that equation. So 1.005 times 10 to the minus 29 kilograms multiplied by 3 times 10 to the 8, and 3 times 10 to the 8 squared, and that gives me 9.04 times 10 to the minus 13 joules. Okay, now that I know from practice is an energy that is in the region of several MeV. Okay, just because I've done EV to joules calculations before, but I need this energy here to actually be in MeV. So I already know that I'm on the right track, but just need to do a few more steps in the calculation. So 1 MeV, 1 EV is 1.6 times 10 to the minus 19. 1 MeV is 1.6 times 10 to the minus 13. So that gives me 5.65 MeV. Now, although I haven't actually used the nuclear binding energy curve in that particular example, I've used the idea from it. If I go back to the previous slide, what I have is originally an americium, which is actually slightly beyond this uranium, and it's releasing an alpha particle, and it's moving down here a little bit. Now the individual nucleons in the alpha particle actually have more energy here, okay, so the mass of the particles is higher up here than it was for the particle that was indeed created. But, okay, so you might be thinking, hang on, how does it have more energy after than before? It's supposed to release energy. Well, it does, but what happens here is the remaining nucleons, and there were 237 nucleons in the neptunium that was produced, they all have less energy. Okay, so this is the average binding energy per nucleon. So that's a huge change in energy there, because it's a huge number of nucleons. So only 4 nucleons gained energy in the form of the alpha particle, and even that wasn't as much as if they'd have been released as free neutrons, but you've got this big energy release. Okay. Now, as a second example, I've done maybe something that looks at the curve a little bit more, and I've said calculate the energy released when uranium-238 splits into 3 neutrons and 2 roughly equal daughter nuclei. Now, to do this, I'm going to look at the curve, and if I look at the curve, these are the basic ideas I had. I had the 3 nucleons here. I had the surprisingly stable here. I had the most stable here. This is iron. And then I had the large nuclei here. So we're starting from uranium-238, which from the graph is roughly 7.5 MeV per nucleon for the binding energy. And then I'm going to have 3 neutrons released. So those individual neutrons, the mass of those neutrons is going to increase quite significantly. Well, not quite significantly, because all of this is quite small changes, but the mass of those neutrons will increase nonetheless. And so we go from here to here for the neutrons, okay? And that leaves me with 235 remaining neutrons to make my 2 daughter nuclei. Now those 2 daughter nuclei are going to be about here. So the nuclei, I'm going to start off with the average binding energy per nucleon being about 7.5 here and going up to 8.5 here. Now those are 2 convenient numbers to work with. So going to just look at the basic idea of taking the energy before should equal the energy after. Energy is still conserved, but now we need to consider that energy and mass are interchangeable. So mass and energy have to be conserved. So I had 235 nucleons after. I had 238 before. And I'm going to release some energy. So this released energy here, that's going to be the energy released in this fission reaction. So 238 times by 7.5, this is 238 nucleons with an average binding energy of 7.5 MeV per nucleon, gives me 1,785 MeV as a total. And on the other side I've got 0 binding energy for the 3 nucleons, and I've got 8.5 for the remaining 2 daughter nuclei. So I said that it was going to be split into 2 and it was going to go to 8.5. So 235 times by 8.5 gives me 1997.5. So you can see that this energy here, the binding energy, is greater than this energy here. Okay, so you have to remember that this binding energy is the energy that is the mass deficit when compared to 3 nucleons. So to go from this heavier mass to this lighter mass is going to release me energy. To go from this lower binding energy to this higher binding energy means that energy will be released. Okay, but I like to think of it as this being the heavy nucleus, not just because of its greater number of nucleons, but the mass per nucleon here is higher than the mass per nucleon here. Okay, and you can tell that because more energy is here in the binding energy. So that energy then gives us some energy release. Now, that released energy is the difference between the 2 sides, okay, which is 212.5 MeV, or mega electron volts. Now, I also did a little cheeky sneak way where I just looked at the change in energy. Now, for my initial nucleons, I'm just saying that that's initially 0, and then if I look at the change in energy, I had 3 nucleons whose energy increased by 7.5, and I'm just going to go back to the graph. So my 3 neutrons, their binding energy went from from 7.5 to 0, and then the rest changed by 1. Okay, they went from 7.5 to 8.5. So that gives me 235 times by 1 is about 235. So if I take this and I say, well, let's start that as it equaling 0. Sorry, this might look a little bit confusing. If I say, well, what's my released energy? Well, I've got that this is an increase, and this is a decrease. So I have 22.5 minus 235 is equal to minus 212.5 MeV. So it's the same result, but looking at it a different way in saying, what is the change in binding energy per nucleon? And I don't think really it matters which way you do it, because it's the same ideas and the same answer, so the same physics. So hopefully that will have helped you with your understanding of nuclear binding energy and mass deficit, and certainly fission. I know I haven't looked at a fusion example, but it would look very similar to this or the previous question, which was the calculations like this. Okay, I hope that helps, and don't forget to look over the video again if you struggled with any of the bits, or watch it a bit slower or a little bit faster if you just need to skim through. Okay, thanks for watching. Goodbye.